This is my second lecture in Chapter 6. It's from the OpenStax, and I want to talk about quantum numbers. There's a whole lot of detail, but I'm going to keep it quite simple. This is the Bohr model of the atom. We previously learned about this, and his model of the atom was that there was an actual electron in a specific orbit around the nucleus, shown here in red. And he used classical physics to explain this, much like the planets going around the sun in our solar system. In his model, the energy depends on the orbit, and the energy is dependent on the charge squared and the orbit squared. N is the orbit number. The quantum mechanical model of the atom has superseded the Bohr model of the atom, and it's really hard to picture this, but maybe this picture best illustrates the strangeness of this theory. It was developed by Schrödinger, I guess, in 1920 during his winter break, and he published his first paper in early 1921, and he developed quantum mechanics. And the atom here is described by mathematics, and it's a statistical model of how electron clouds are in an atom, and it's described by 4 quantum numbers, and it's currently the best model we have. This is the first quantum number. It's called the principal quantum number, and it's given this symbol n. Now, n can take on integer values, 1, 2, 3, and so on. But it cannot be 0, and it can't be half or fractional amounts. N represents the main energy level, or shell, of the electron in the atom. And one way to think about this is that, for example, here on the graph, we see that an electron in the n equals 2 orbital is further from the nucleus on average, and therefore higher in energy than an electron in an n equals 1 orbital. And these orbitals, as we'll see, are just electron clouds. But this is a cross-section showing the statistical nature of the distribution of where you might be able to find the electron. The second quantum number is called the angular momentum quantum number, L. L represents the shape of the electron cloud or orbital. So there's nothing really orbiting. There's just the electron that's smeared out and takes the shape of different things. We sometimes refer to it as a dumbbell, or possibly a sphere, or even a clover leaf. Now, L represents the shape of the orbital. In this figure, you can see how there's a fuzzy electron cloud. If you were to take a picture 1,000,000 times and superimpose all of those pictures, you would see dots representing the possible positions of electrons all over the place. So here's a contour plot just showing the 90% probability of finding the electron within that shape, and this is represented as a sphere. What happens when n is equal to 2? L can have values from 0 all the way up to n minus 1, so possible values are L equals 0, which is described by a spherical s orbital, or L can be equal to 1, and this is represented as a p orbital. So L equals 1 is a p orbital, and it's shown here as sort of a dumbbell shape along the xy axis. When n is equal to 3, there are 3 possible values for L. L could be 0, or 1, or all the way up to 2, which is n minus 1. So L equals 0 is a s orbital subshell. L equals 1 is the subshell that describes the p orbital we previously saw. And L equals 2 is a very complicated shape, kind of shown as a clover leaf. That's the best kind of macroscopic object we can refer to. It's shown here on the right. So that's a d orbital. The third quantum number is called m sub L, or just m in some textbooks. And this is the magnetic quantum number, m sub L. Now the values of m sub L depend on L. M sub L represents the orientation around the nucleus of these variously shaped orbitals. Now, m sub L can have values from negative L all the way up to positive L and whole numbers in between. So let's look at what happens when L is equal to 0. Remember, that's referred to as the s orbital, which is spherical shaped. ML can have values of, well, just 0. And that kind of makes sense because there is only one orientation for a sphere in three-dimensional space. When L is equal to 1, remember again, we call this a p orbital. These are these dumbbell-shaped electron clouds. So when L is equal to 1, then M sub L can have values between -1 and +1 and 0 in between. So it can have values of -1, 0, or +1. And these are three different orientations for a dumbbell-shaped electron cloud. And that sort of makes sense because you have the x-axis, the y-axis, and the z-axis. So here are the three different orientations of a p orbital on our familiar Cartesian coordinates. Things get a little more complicated when you get to the higher subshells. So when L is equal to 2, remember again we described that as a d orbital, which is kind of shaped like a cloverleaf. ML could have values between -2 and +2 and all the numbers, integers in between. So it could have values of -2, -1, 0, +1, or +2. So there are 5 different d orbitals, as they're orientated or whatever in three-dimensional space. Now 4 of these kind of look like cloverleafs, and one looks very strange, like a dumbbell inside of a donut type of shape. So there are 5 orientations or 5 types of d orbitals, and the math's highly complex, and I don't want to get into that. The fourth quantum number is the spin, or m sub s, or s for short. And the values of m sub s are independent of anything else we've talked about. Anyway, the electron can have m sub s values of +1/2 or -1/2. And you can kind of think of the electron as a spinning top. What's interesting about a top is that it can spin this way or spin this way. And just like the electron could be kind of visualized as having a spin up or down, so can a top. So this would be like spin up, the normal way in which a top spins. All right, that would be with the spindle up, for example. And an electron can also spin down, and that would be like this with the spindle down. So if I give it a flick, you can see how the top spins the other way. Okay, just like that, the electron can have 2 different spins. So +1/2 is oftentimes referred to as spin up, and we sometimes indicate that with an arrow pointing up. Or the one on the right here, we can see that the spin is -1/2, and you can think of that as spin down or an arrow down to denote that. Interestingly, this does not come from the Schrödinger equation, but rather from experiments. So we call it the fourth quantum number anyway, or at least I do. So that's the 4 quantum numbers. You've got N, L, M, and S.